My name is Gustavo Espinosa, and this is Lab 4, Circuits and Capacitors. The purpose of this lab is to understand the behaviors and effects of resistors in series and in parallel, and also to use multimeters to measure the potential differences and conventional current. The main physical principles that we will be dealing with in this lab are energy conservation, Ohm's law, which states that voltage is equal to current times resistance, capacitance, which is equal to charge divided by voltage, the node rule, which states that the current in is equal to the current out, and finally the loop rule, which states that the potential differences in the entire system will always be equal to zero. The first circuit that we will be dealing with consists of two 9-volt batteries, two ammeters, and two different resistors equaling 147 ohms. We can use Ohm's law in order to predict the current through the system, which is equal to 0.0204. The actual current, however, that is measured is equal to 0.02 amps. And when we reverse the ammeter in the system, we get negative 0.02 amps. Next, we will be measuring the potential difference in place of where an ammeter was in the previous circuit. The potential difference found in that spot is found to be 3 volts, and the remaining ammeter measures a current of 0 amps. This makes sense because there's a 3-volt potential at the battery and a 0-volt potential at the resistor, resulting in a total potential difference of 3 volts in the system. Next, we measured the potential differences at different checkpoints around the circuit. On the right is a diagram of the different checkpoints, and on the left is a list of the measured values. To find the total potential difference of the circuit, we add up all the values found, and we see that it is equal to 0, which is in line with the loop rule. If we plot the potential differences on a graph based off of the different points in the diagram, we can see that the potential difference increases as it passes through the two batteries, and then decreases as it passes through each of the resistors. As you can see, it increases a lot more when it passes through 100 ohm resistor versus the 147 ohm resistor. Next, we measured the current with an ammeter in parallel to one of the resistors. As you can see, the reading moves from 2 amps into 6 amps. And this is because when the ammeter is in parallel with the resistor, the current is going to flow through the ammeter more because of its less resistance, in line with V equals IR. As resistance decreases, current increases. Now we can calculate the resistances along the circuit using Ohm's law, which is delta V is equal to IR. We can use the values of current and resistance found using our ammeter in the circuit. Using those values, we get slightly different values of resistance versus the true value, and this is because of lack of precision in the ammeter. However, the zero resistance in the wire and ammeter makes sense because of our assumption that these two components have zero resistance. Now we will be working with capacitors using the circuit with the following components: one 9-volt battery, one 200 mF capacitor, a 10 ohm bulb, and a 20 ohm bulb. When we first turn on the circuit and the capacitor is at zero charge, the light bulb is at its maximum brightness. However, as time goes on, the light bulb dims until eventually turning off. This is because as the capacitor charges, the overall current slows down, and as it reaches its maximum charge, the current will slow down to 0, therefore turning the light bulb off. The time at which this happens differs from the resistance of the light bulb, and as you can see, the doubled resistance of the light bulb results in a double time to charge. When we disconnect the battery of the circuit and simply have the capacitor, we can see the same behavior in the light bulb, as it starts off bright and slowly dims until fully turning off. This is because as the capacitor discharges, the current will slow down as time goes on, and these discharging rates are shown below. And again, we can see that the 10 ohm light bulb discharges in half the time as the 20 ohm light bulb. Next, in order to determine the time constant in this circuit, we plotted the first 20 seconds of the capacitor discharging, as well as the values of the potential difference found. In order to determine the time constant, we linearized the data by plotting the natural log of V over V naught versus time, and found that the slope is equal to negative 0.167. Now we could use this slope and the relationship to the time constant, which is equal to negative t over RC. And if we take the negative reciprocal of the slope found, we find that RC is equal to 5.99 seconds. Finally, we have some reflection questions. The first one being, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it affect your results? An ideal ammeter has zero resistance, however in real life, all ammeters have some resistance, resulting in the readings being less than true. The second question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? And ideally, a capacitor would charge instantaneously. However, because all components of the circuit actually do have resistance, time is required to charge the capacitor.